Okay, I'll start with a little about expanders. So the classical expanders are highly connected, preferably sparse graphs. So we want, for example, a graph which cannot be partitioned easily. So if I take any partition of the vertices, I have a lot of edges crossing between between the blocks. And one way to define it is the Chigger constant, which is the minimum over all partitions of the number of edges crossing divided by the sizes of the partitions. We don't want a trivial partition into one edge and everything else. And we'd like to normalize this to make it scalable. So this is the Chigger constant. And we want expanders to have large Chigger constants, so graphs that are stable. We can't cut them easily. And spectral graph theory gives a nice answer to finding expanders. The Graph Laplacian is the operator which, for a vertex, this is the Laplacian. For any function on the vertices, it gives to each vertex the original value multiplied by the degree, which is the number of neighbors, and minus the values over the neighbors. Now, if I have a constant function, then this is 0, because fv is the same of f of w everywhere. But actually, also for a locally constant function, this is the same. I don't need it to be constant. I only need every two neighbors to have the same value. So this actually means, and this is if and only if. So the kernel of the Laplacian are the locally constant. And if we're interested in the spectrum of the Laplacian, but as we said, the constants are not very interesting. So we look at the orthogonal complement of the constants. And this is the functions which sum to 0. So this is the interesting spectrum. We call the minimal value the spectral gap. Of the graph. And what we says here is basically that lambda is 0 if and only if the graph is disconnected. We can find the function with sum to 0 and is locally constant if and only the graph is disconnected. So now we would like to say, okay, disconnected is the worst thing we can have. We want it to be very connected. So maybe if it's very big, is it expander? And yes. So what we have is something of the form, the Chigger constant is at least the spectral gap. And this is again bounded by a function of the Chigger constant, where k is the degree, the maximal degree in the graph. So this is the discrete Chigger inequalities due to several people, some of them sitting here. And they call Chigger because of a similar result in Riemannian geometry, which relates very similar thing over Riemannian manifolds. Maybe I'll get to them later. What we want is to do all of this in high dimension. So there are several ways to generalize this, and people are studying them and the connection between them. What I study starts from Ekman's idea of discrete Hodge theory. And so we have a d-dimensional complex, simplicial complex, and we look at the chains in every dimension. And the cochains. So this is ancient. We have a boundary map which gives to a chain its boundary. And we have a co-boundary map which gives cochain its differential. And what Ekman said was, we want to identify these, like in Riemannian geometry. If we have a Riemannian metric on a manifold, then we have a pairing between forms and vector fields. So we introduce a Riemannian, a discrete Riemannian metric. So for two functions, we just define something, and it can be very general. So the simplest thing would be go over all cells of dimension I. Let's say if f and g are in Ci or Ci, then this would be an inner product. This would give you an identification. And then you can start doing spectral analysis. And it turns out that if you go like this, so codifferential and then differential and then back, you get the graph Laplacian. So this is an easy exercise. So let's call this the zero Laplacian, and similarly we have the edge Laplacian, and so this will be the vertex Laplacian, edge Laplacian, triangle Laplacian, and so on. And again, we have, because this is a cochain complex, if we come from C0 to C1 and we take the Laplacian, it will be already 0 here. So the image of the coboundary map from Ci minus 1 to Ci is trivially in the kernel of the ith Laplacian. So this is not interesting, and we want to look at the spectrum of the Laplacian, the ith Laplacian, restricted to the orthogonal complement. The orthogonal complement of a map is the orthogonal complement of an image of a map is the kernel of its dual. So these are the cycles in dimension I. Like for graphs, we had the function which sum to 0. Oh yeah, I should put here the -1 to take the augmented complex too. So this would be really the cycles. If I put here C minus 1x, then this is the augmentation map which take a function to the sum of the values, and then this is the cycles. And again, let's say that the lambda I is the minimal value, and we want to say now to connect this to the combinatorics of the complex. So first thing we can say, and this was Ekman's motivation, is that well, when do we have zeros here? Zeros here come from the kernel. I have the ones that come from a dimension below, but they could have extra ones. So the kernel of the Laplacian, the ith Laplacian, is actually the kernel. Because these are dual maps, it is the same as the kernel of D, which are the cocycles. So I have kernel, non-trivial kernel. Non-trivial means that it intersects the cycles. And we said, as we said, this is if I have forms which are both cycles and co-cycles. We call these harmonics. And having co-cycles which are not co-boundary just means that we have homology. So harmonics in dimension I is the same as non-trivial cohomology in dimension I. In particular, lambda I is 0, again, if and only if we have non-trivial cohomology. So this was Ekman motivation, and we want to do combinatorial stuff with it. And it turns out you can do a lot of things. It's not clear how much. But I'll give you an example of the easiest results we have. So now we have a d-dimensional complex. If we go over all partitions of the vertices now to d parts, and look at the number of d cells which have one vertex in each block of the partition, and again normalized, and again divided by the size of the blocks. So let's call this the I-Chigger constant. Then again, we have the same thing. We can prove Hi is at most lambda I. So this is again combinatorial parameter.
Yeah, I is D.
I is D minus 1, yes. So yeah, you can do it for any dimension. Oh, and I didn't say, for this, I need to assume something quite strong. The reason that I didn't take a general I is that for this result, I need to assume that everything in dimension, in codimension 1 and below is trivial, which I mean it's everything. It's all the vertices. So if the codimension 1 skeleton is everything that it can be, then we have this nice result. Oh, okay, so that so this is the next thing I wanted to ask. What do we have here? So first of all, it's not as easy as in the graph case. We have a simple example. The Möbius strip has H1 5/4 and lambda 1 0 because the homology of the Möbius is like that of a circle, which is non-trivial. So I have non-trivial first homologies, and this you need to compute, and it's not 0. So thing will not be as nice as in the graph case. You won't have something like this, but we have numerical evidence to suggest that yes, there should be something here. What?
What if you had orientability?
That was also our first guess, but I think nothing came out of it. I'm not sure we have a counterexample, but we couldn't use it. So this is one question I'm interested in. Can we do something on the other side? Another question in this direction is, can we take everything back to Riemannian geometry? So can I use the spectrum of the Laplace operator acting on smooth I-forms on a differential manifold to say something on the geometry of the manifold? So there are very little results about this. The one result that I know is that you cannot take the lambda I of a manifold and relate it to the standard Chigger constant, the zero-dimensional Chigger constant of a manifold. This is the result of Courbois and Courtois. But there is the problem is that there is no Hi, so you need to find an interesting definition which generalizes this to be able to ask anything at all. And
also, the Laplacian is somewhat different in Riemannian geometry. One uses the delta plus delta.
oh, you go also in the other direction. Yeah, that's a good point. In Riemannian geometry, you also you do this and add this, and then you don't need to restrict to you don't need the restriction to to the cycles, because the cycles are being taken care of by this part. But when you look at the combinatorics, they really do different things. What happens here and what happens here is different stories. You want to study each of them separately. They don't even live in the same scale. So you look at the spectrum here, and it might be clouded by something from here. How much time do I have?
Well, 2 minutes.
2 minutes. So the examples I've been working on lately are, I just say a word, are the Ramanujan complexes, which are good guesses for high-dimensional expanders. So graphs, Ramanujan graphs, are one for which the spectrum of the vertex spectrum looks something like 0 for the constant, then possibly 2k for the two colorings. If a graph is too colorable, then you have the 2k. And a k regular graph is too colorable, then you have the 2k eigenvalue corresponding to 1 on one side and -1 on the other side. And everything else is very concentrated. So around k, everything is in a strip of width 2 over k minus 1. And so here you have expansion. And here you have also a large gap from the end of the spectrum, which also gives nice combinatorial properties. So what happens in higher dimensions? So now we understand triangle complexes pretty well. So Ramanujan triangle complexes have the edge spectrum look something like this. They have 0 corresponding to co-boundaries. Then they have 3k. K again is the degree. So here you could have 2k and you could not have it. Here you always have the 3k, and this caused problems for people who try to understand this. And you have this nice strip of with the same thing, √2 root k minus 1. And you have another strip around 2k, which is very, very narrow. It looks like 8 here and 1 here. 2k minus 8, 2k plus 1. And you have most of the spectrum is here, but you have a small part here. I should say that this is already, this was known to Garland. This is work from '73. And he was interested in the Hodge theory. He wanted to show that the cohomology is trivial. So he gave a lower bound for the spectral gap, which gave trivial cohomology. And later on, people understood that his argument is purely combinatorial. It's very beautiful. He just looked at the local picture of a manifold. He calls it the p-adic curvature. And he has some insight from geometry, which relates this local curvature to the global behavior, the global Laplace eigenvalues. And he showed actually a tight bound. He really gets this bound. But then people realized that his argument could also work from the other end of the spectrum. But for other complexes, it's interesting. For Ramanujan complexes, you're stuck because of this 3k. So in order to really understand that the spectrum is interesting, it's inside two narrow strips. You need a lot of machinery that wasn't available there, a lot of works in representation theory. And then again, we can do combinatorics, etc., etc. Thank you very much.